In this lecture, we're going to introduce the concept of Lewis acids and bases, which is a broader definition of acid-base in Bronsted-Lowry. So we've had Arrhenius's definition, which just focuses on protons and hydroxide ions. And then we've had the Bronsted-Lowry definition that we've been using the most, which is proton donor or proton acceptor. Well, a Lewis acid-base definition is even broader still. And so it's a larger umbrella that still includes all of our acids and bases as defined by Bronsted-Lowry or Arrhenius. In a Lewis acid-base, Lewis acid is going to be a lone pair acceptor. Now, this is instead of donating H+, it's going to accept a lone pair of electrons. And a Lewis base is going to donate that pair of electrons. So when we think about something like NH3 forming having an acid-base reaction with strong acid, that lone pair creates a bond to that H+, and so it's really donating that lone pair right there. So it just like our Bronsted-Lowry definition, that Lewis base must have a lone pair of electrons that it can actually donate, that can give away and share. So that doesn't change too much. So the real difference then in this definition comes down to how we think about Lewis acids. And in this definition, a Lewis acid must have an empty orbital that's willing to accept an electron pair. So in our example over here that we're used to, it's that H+, right? So we had a hydrogen with one electron that was in a bond, let's say, to something like chlorine. And when this bond's broken, these two electrons stay with the chlorine and the hydrogen leaves. And that really leaves this empty, sorry, it's a 1s orbital. Going back to 161, you have this empty 1s orbital that can accept electrons when it forms this bond with the electrons from the nitrogen in this case. And so that hydrogen cation is basically just an empty s orbital that can accept those electrons from the base. There are other types of things that have empty orbitals that we'll look at as well, and those also will count as Lewis acids, even though they won't have a proton that they, or a hydrogen that they donate. So then these are going to be typically electron deficient in some way. This might not just be because they've lost, broken a bond. It might be because they're just attached to something so electronegative that it essentially is electron deficient from that difference in electronegativity. Or it might not have an octet as well. So there's an empty orbital that way. So typically where we see these for Lewis acids, these are usually going to be molecules or ions that have incomplete valence shells. Or it's going to be molecules or ions that have multiple bonds that can be shifted around to make room for more electrons. Or they're going to be ions or molecules that have central atoms that can actually expand their octet. Remember, that's anything in the third row or below on the periodic table because they'll have empty d orbitals. So it's a lot of different elements. Our Lewis base is going to be anything that has that unshared electron pair, which is similar to how we've been thinking about bases so far. So the real kind of shift in thinking comes when we look at our Lewis acid. So again, going with our definition that our Lewis base donates an electron pair and our Lewis acid accepts the lone pair. Let's look at a Lewis acid base pair. So here we have our Lewis base, which is our ammonium that we've talked about already. It's got that spare electron lone pair that it can donate. And then we have boron, and boron tends to have, it has a 6 valence electrons in, and it doesn't complete an octet. And so it has an empty orbital in it, in this compound. And boron is a metalloid, so it behaves a little bit differently than a nonmetal. And when it forms covalent bonds, it typically forms them so it only has up to 6 valence electrons around it. So in this case, that lone pair can actually be donated into boron's empty orbital right here and form a new complex. And with Lewis acid bases, we call these complexes coordinate covalent complexes. That's kind of a terrible color. And so we now have a coordinate covalent complex here that is formed between our Lewis acid and our Lewis base. The other name that we have for this that you'll see is adduct. So the product of a Lewis acid base reaction would be an adduct. Let's look at another example. Here we have a Lewis base. That's a hydroxide ion. It's got lone pairs that it can donate to another compound. And then our Lewis acid is going to be carbon dioxide. So in this case, carbon does not have an empty orbital at all. It has an octet. It is complete. But it does have multiple bonds that can shift around. And so because of that, we're going to, this will be defined as a Lewis acid. That electron pair from oxygen is going to be donated to the carbon that'll move electrons tied up in a double bond to the oxygen up to become a new lone pair. And so you end up with this single bond here where it used to be a double bond, and you've created this bond between the oxygen and the carbon. So the carbon still has an octet and it still has 4 bonds to it, just like it did in carbon dioxide. But now those electrons that were in bonding electrons before are now lone pair electrons on an oxygen. And then this is our coordinate covalent complex right here, or we can call this our adduct. So I realize in my example, I already have labeled this, but let's walk through it anyway. Identifying Lewis acids and base pairs. And so our Lewis base here is at NH3 because it has a lone pair on the nitrogen. And our Lewis acid is that H+. It has an empty 1s orbital that can accept that electron pair. And that then forms an adduct that is NH4+. And now this occurs, we can do this without water technically, or with water still. So looking at another one, we have F- is our Lewis base in this reaction. It has lone pairs. It has 4 lone pairs that can be donated. And then we have BF3 as our Lewis acid. And this has 6 electrons in its valence in the covalent compound. So it has room, it has an empty orbital that can accept that lone pair of electrons from the fluorine to form BF4-, which would be the adduct.